Different formulations of DNS-based Eulerian-Lagrangian models have been reported in the literature. Here we will focus on two of them. The former, called fully resolved, is valid when the particle size dp is much bigger than the Kolmogorov length scale L small lambda. On the grounds of what stated before, dp is much bigger than the size of the computational cells for the fluid flow simulation. In the fully resolved method, the Navier-Stokes equations are resolved in the volume actually occupied by the fluid. Therefore, the fluid domain changes in time due to the fact that the solid particles are moving. Under the simplifying assumption of negligible particle-particle interactions, the solution procedure is as follows. First, at a given time, the Navier-Stokes equations are solved in their own fluid domain. Second, the force exerted by the fluid on each particle, F from F to P, is calculated by integrating the pressure and shear stress distributions over the particle surfaces. Third, the positions of the particles at the end of the computational time step are obtained by numerically solving the particle equation of motion, which, under the assumptions made, takes the following form: particle mass times particle acceleration, mp times dv divided by dt, equal to the gravity force on a particle, mp times g, plus f from f to p. Fourth, the fluid domain is updated and the procedure is repeated. At the opposite extreme, point particle DNS is applicable when the particle size dp is much smaller than the Kolmogorov length scale L small lambda. In this approach, the fluid domain covers the entire space, and the presence of the particles is accounted for indirectly by solving for a modified formulation of the Navier-Stokes equations. Assuming the particle concentration to be sufficiently small, such modified formulation consists in adding to the already discussed Navier-Stokes equations point sources at particle positions, representing the forces per unit volume exerted by the particles on the fluid. From a mathematical point of view, this is 1 over the volume of a cell, W cell, times the sum for I from 1 to the total number of particles in that cell, MP cell, of the force exerted by particle I on the fluid, F from Pi to F. Note that for the action-reaction principle, F from Pi to F is equal to minus F from F to Pi, which is the force exerted by the fluid on particle Pi. Unlike in the fully resolved approach, F from F to Pi cannot be obtained by integrating the pressure and shear stress distributions over the particle surface, since the computational mesh is too coarse to provide all this information. In fact, the fluid dynamic characteristics of the fluid are calculated only at the center of the computational cells. Therefore, this quantity has to be estimated from the only information available. This is achieved by employing the force models illustrated when discussing the particle equation of motion, namely drag force Fd, pressure gradient force Fpr, buoyancy force Fb, and so on. Let us focus on the drag force, which represents the dominant contribution in most particle-laden flows of interest in this course. It has already been explained that the drag force acting on a particle can be expressed as 1/2 times the density of the fluid, or F, times the drag coefficient CD, times the area of the particle cross-section, pi times dp to the square divided by 4, times the absolute value of the relative fluid particle velocity times the relative fluid particle velocity. The relative fluid particle velocity, in turn, was calculated making reference to the unhindered fluid velocity u at p, that is, the fluid velocity that can be hypothetically extrapolated to the particle centroid, whilst neglecting the disturbances caused by the particle itself. In the point-particle approximation, u at p is obtained from the interpolation of the known u values at the nearest cell nodes. In the solution procedure, the calculation of the flow field, the integration of the particle equation of motion, the update of the particle position and velocity, the evaluation of the unhindered fluid velocity, and the determination of the source terms in the Navier-Stokes equations are repeated in a time loop.